Okay, guys. Okay, let's start with the May-June 2020 paper. Okay, so for question number 1, so we have this transition metal question. Okay, so an aqueous solution of cobalt 2 chloride. Okay, they have given that it contains this complex ion. Define the term complex ion. Now, when you want to define a term of complex ion, so do remember it's going to be a molecule, or it can be also ion. So in this case, we can say a molecule or ion. Better in this case, ion, right? So they say an ion, okay, an ion, okay, which has central atom, okay, or ion. Yeah, in this case, I think better to say which has central ion, okay, surrounded by ligands. Okay, so what are the marks? Okay, the marks they would like to see the central ion and as well the ligands. Okay, please take note of that. Now, sample of this, okay, are reacted separately with aqueous sodium hydroxide and with excess of aqueous ammonia. So please remember, okay, that your cobalt ion, okay, the complex ion is always going to be pink in color. Okay, this is very important. It is pink in color. Okay, and then you are reacting with aqueous sodium hydroxide and aqueous ammonia. Now, if you react with sodium hydroxide, I have written over here, okay, you are going to get cobalt hydroxide. Now, cobalt hydroxide, okay, this is pink, okay, the cobalt hydroxide is going to be blue precipitate, and this precipitate, when you warm it, okay, if let's say you are using sodium hydroxide excess, okay, if you warm, it will change into red. Okay, but in this case, okay, I'll just leave it over here. This one is going to be extra notes for you. Okay, but to answer the question over here, okay, the reaction with aqueous sodium hydroxide, the color and state the cobalt containing species. Okay, the color is going to be blue. Okay, and then the state is going to be precipitate. So they want to know whether it's going to be blue precipitate or blue solution. So in this case, this is precipitate. And then the ionic equation, so you just write down COH2O6, 2 plus, okay, plus OH minus, okay, to give you, because I don't want sodium hydroxide, we want ionic, okay, so to give you cobalt hydroxide, solid, okay, plus all the remaining H2O has been removed, okay, so it's going to be 6 H2O over there. Okay, this is going to be everything that is going to happen, but just check, okay, OH you need 2, so you need to put 2 there. Okay, so this is going to be your ionic equation. Now the type of the reaction that is happening, because there is going to be, this is aqueous, okay, this is aqueous, this is solid, and this is liquid. Because there's a solid that is being formed, so you just say type of reaction is precipitation. If you want, okay, if you want, this is also what we call as acid-base reaction, to give you salt and water. If you want, you can also do that, okay, but I think the best way is to represent it as precipitation reaction. Now the reaction, okay, the reaction is going to react with excess aqueous ammonia. Now the excess aqueous ammonia, so I have written over here, if you have ammonia, okay, all the ammonia ligands, okay, will replace, okay, the water ligands. Okay, all the ammonia ligands will replace the water ligands. So you are going to have the color that you are going to actually observe over here. Okay, the color that we are looking is going to be a blue solution. Okay, so it's a blue solution. It's not going to be a precipitate. So please remember this. Okay, it's going to be blue solution. And then the ionic equation is going to be, you are going to have something like this. 6 ammonia, you are going to get cobalt. Now, Jody, can you tell me whether what is going to be the charge? Okay, is the, here, why the charge? Okay, you can see here, why is going to be 2 plus? Why is not going to be neutral, Jody?
And H30, yes.
Yeah, and to be exact, H2O was 0. Okay, H2O was 0. So it's cobalt 2 plus. So when you replace with NH3, yes, NH3 is also 0. So the 2 plus will stay. Okay. So this one, please take note. Okay. So this reaction is going to be exchange of ligands. Okay. The ligands that are involved will be water and ammonia. So we call it as ligand exchange. Okay. Done. Now, furthermore, okay, related to cobalt, okay, when concentrated hydrochloric acid is added to a solution, okay, of cobalt this, okay, a blue solution is formed, okay, and the following equilibrium is going to be established. So you see here, when you are adding with sodium hydroxide, you are going to get a blue precipitate. When you are adding with ammonia, you are going to get a blue solution. When you are adding with the hydrochloric acid, you are going to get a blue solution. So please remember all this. Okay, in this case, use LCP principle, okay, to suggest the expected observation when silver nitrate solution is added. Now, silver nitrate, they are going to react with the Cl minus to give you silver chloride and precipitate. Silver chloride is a white precipitate. So in this case, what happens here is going to be you are removing the Cl minus. If you are removing the Cl minus, what happens? Okay, according to LCP, you do not want the Cl minus to be removed. So you need to counter react the situation by shifting the position to form more Cl minus. So the position of the equilibrium will be shifted to the left. So here they say suggest what is going to be expected observation. One observation is going to be because silver chloride is being formed, you can just say a white precipitate is formed. Okay, that's going to be the first one. Second is going to be, we know this is going to be a blue solution. If it is going to move to the left, the blue solution is going to be not going to be formed. You are going to form more of this. Okay, and this color earlier I mentioned to you. Okay, cobalt. Okay, in this form they always exist in pink solution. So you are going to get the solution to turn to become more pink. So you can actually say the solution change from blue to become pink. Okay, the solution change over there. And then you can say also, okay, because it's 2 marks, okay, you can also say the position of the equilibrium is shifted to the left. Okay, position of the equilibrium shifted to the left, which will actually explain this part, okay, if you want. So but any of the two responses over here will be given the marks. So any two, okay, so you need to explain. So I think when it comes to explaining, you need to still mention about this. Okay, you still need to mention about the position of the equilibrium, what happened because of the white precipitate is formed. You are going to reduce the Cl concentrations, a chloride ion concentration, and then the position will move to the left. So you don't have any choice. Okay, so you still need to actually write down. Now for this one, okay, because we are discussing about cobalt, okay, ions, okay, I still want you to go and refer to my video, okay, on this ligand substitution for complex transition ions. Okay, so this is the exact title. Okay, maybe later I will actually put it, if I upload this video, okay, then I put it in the description, or I will send it in the WhatsApp group as well. Okay, I have discussed in the, I think, 10 minutes video, okay, about all the equations involved for the ligand substitution. So in this particular question, we have discussed 3 equations involving cobalt. So you still need to actually learn about copper. Okay, so please watch that video about copper. Okay, so in this case, you can see, okay, how many marks given just for this. Okay, you see 1, 6, okay, and 2. Okay, so you are roughly looking at 9 marks, and they didn't stop over here. Okay, if they want to continue with copper, they can continue and asking more. Okay, but instead of doing that, they straight away go for introduction to organic chemistry, or more towards your A2. If you look at it, it's going to be stereoisomerism for complex ions. So they ask you, okay, they mentioned that this complex can show stereoisomerism, complete 3-dimensional diagram to show 2 isomers, okay, of this. This one is going to be slightly different than what we normally do. because it's going to have three ligands each. So this one definitely the shape is going to be octahedral. Okay, that is confirmed. Okay, but the way that we draw, okay, so if I just put it in this way, so if I just put it here, okay, if I put it like this, okay, I am going to expect to see, okay, so something like what we don't have any choice like putting in. If you have NH3 2 Cl4, then it's easier. Okay, it's easier. I can put the ammonia up and down. Okay, but in this case, it's going to be slightly complicated. So I will actually put the ammonia here, NH3 here, and then ammonia here. Okay, and one of the ammonia needs to be put somewhere. Okay, so you need to decide, okay, where do you want to put. Okay, so in this case I will decide to put the ammonia maybe somewhere here. Okay, so I will put it here, and then the remaining Cl I'm going to put it them over here. Okay, so this one is going to be they are appearing side by side to each other. Okay, if I actually put it, okay, ammonia here, okay, and then Cl here, if I put, okay, the remaining Cl, okay, if I put one Cl here, another Cl there, and then ammonia here, another ammonia here, you can see that, okay, what happens here. Okay, I think even it will be better if I show it like this here. I think if we can actually show similar to this, so maybe I'll actually show somewhere here. Hold on. Yeah. The idea is to show whether they are cis or trans. So I will actually put it here, NH3 and then Cl. So I will put the ammonia side by side here, and then Cl side by side here. It's much more easier to see. But if you look over here, there is two ammonia here, and then one ammonia across. Okay, two chlorine, another one across. So this one is going to be more towards cis and trans. Okay, they didn't ask. Okay, it's a bit complicated. So the type of isomerism is going to be geometric isomerism, or you can actually say cis or trans. Okay, so this is how you draw. Now, one thing that I want to highlight over here is going to be the way you show. Okay, the way you show. Okay, this is okay when you just simply do it for your revision. But now I think we need to practice about how to show them. Okay, if it is coming out, okay, from the from your iPad or coming out from the paper, okay, it's supposed to be something like this. And then, okay, replace with the dotted line. Okay, so probably something like this. If you can just put, okay, you can refer to the marking key. So this is going to be the type of stereoisomerism that it can form. Okay, I'm very sure we have discussed this question before last time. Okay, please take note as well. Okay, this is going to be something that you need to see or visualize. Okay, so the best way is to look at it. You just put ammonia and Cl here, ammonia and Cl, and then you put all the ammonia at one side here. Okay, so they look like cis. Okay, so here if you put one, okay, here, and then put them across, okay, that will look like trans. Okay, now let's continue. Compound X is going to be tetradentate. Tetradentate means they are going to able to form four bonds. Okay, four of the lone pair can be donated, okay, to the metal ion. So suggest why one molecule of X can form four dative bonds. So when I see this, there's nitrogen. Nitrogen has one lone pair, one lone pair, one lone pair, and one lone pair here. So they have, okay, nitrogen, okay, four lone pair, okay, which is going to be available for bonding. So that will be the answer for this. Okay. The next question is, okay, this compound, okay, they react with cobalt 2 ions, okay, with 1:1 ratio to form a new complex ion. So construct an equation for this reaction. So I've done it earlier. Okay, so what I feel like cobalt. Okay, cobalt. You are something similar with the previous example. This cobalt, the 6 water will come out. So water is going to be neutral. So it's going to be still CO2 plus, and then going to be replaced by this tetradentate ligand. This tetradentate ligand is also going to be positive, zero charge. Okay, so when they come in, okay, they are just going to join this, and do not forget about the 2 plus. The 2 plus is going to be staying, because why? This is going to be neutral. So the charge is going to be zero. So when you add, okay, you are going to get this, and then the 6 moles of water will come up over here. So that's going to be the equation for this reaction. So this one maybe takes time to visualize, but do remember they are going to form 4, okay, 4 bonds. Okay, so cobalt, okay, then straight away 4 bonds. There's no need to show, okay, but the important thing is when this 6 moles of water goes out, the charge 2 plus stays. Okay, and then when they come in, the charge also stays the same because they are neutral. So if you actually put this as without the charge, you are missing that 1 mark. Okay, you won't get that 1 mark. So you see how they have actually done this question. Okay, they have given you, asked you about complex ion. They tested you on the equation. Okay, they have tested you on the stereoisomerism. I think they given something a little bit tricky over here for this particular paper. And then they ask something simple. Okay, but you see why and so on. Okay, they just want to test your basic understanding of this, and as well as this. Okay, in future, don't be surprised if you have with the ratio of 1 to 2. Okay, or something for different ligands. So this is something that we need to also expect. Okay, so this one, please take note. This is some of the ways that they can actually ask question. Okay, the next question is going to be question number 2, which is very, very important. Yeah, this is what I want to actually highlight every single time when we learn lattice energy. When you revise your lattice energy, this is something that you really, really, really need to take note. Okay, please remember this. Okay, so describe and explain the trend in solubility of the group 2 hydroxide down the group. If they ask you this question in your AS, they will just say describe or state the trend of solubility of group 2 hydroxide. Your answer will be the solubility will increase. That's it. They will not ask you to explain. This is only going to happen in paper 4, okay, which is going to be your knowledge about lattice energy, hydration energy, and solubility. Okay, so in this case, okay, please remember this. Okay, in your AS, we have learned that solubility of hydroxide going down the group, solubility increases. Okay, but in sulfates, okay, sulfates going down the group, solubility decreases. How to remember that? Okay, just remember magnesium sulfate and then barium sulfate. In chemistry, if you do not know what is going to be the color of barium sulfate and what is the state of barium sulfate, then something wrong with you. Yeah, so please take note. All chemistry students must know that barium sulfate is a white precipitate, one of the basic requirements for a chemistry student to know. And do remember, if this is white precipitate, of course, the one that is top, which is going to be magnesium sulfate, they are aqueous. So from aqueous to change into white precipitate, you can clearly see that there is going to be decrease in the solubility. Okay, they are going to form precipitate. So please remember this. This is going to be in your AS. Now, when they ask you to explain, okay, now we focus on the OH. They say explain the trend of the solubility of group 2 hydroxides down the group. Now, how to explain? Okay, this is related to the formula. Okay, but explaining, I think no need to use the formula. Okay, this one is going to be what I told you to remember. Let the soul go and hide. Okay, if you can remember that. Okay, lattice energy, let the soul go and hide because they are going, so it's going to be negative. I put it over there. Okay, but whatever it is, okay, this is going to be the relationship between them. Okay, or if you just want the solubility, the solubility is going to be lattice plus hydration. Okay, do remember lattice energy and hydration, they are both negative. Okay, they must be negative. Okay, lattice energy and hydration, they are negative. But the solubility, okay, the solubility is going to be, can be either positive or negative. If your value is going to be negative, okay, it's going to actually tell us that this is going to be soluble. Okay, this is very important. If your enthalpy of solution is going to be negative, that is going to tell us about, okay, this is going to be soluble. Okay, please remember this. So now how do I relate with this? Okay, going down the group, okay, you are going to have, okay, your lattice energy and your hydration. Because of the size that is increasing, the ionic radius that is increasing, they will make the enthalpy of lattice energy and the enthalpy of hydration to become less exothermic. Okay, they are going to become less exothermic. And which one changes more, or which one become more or less exothermic? Okay, so in this case, okay, you need to compare lattice or hydration. In this case, for hydroxide, the lattice energy changes more. Okay, the lattice energy changes more. Explanation is basically M2 plus, okay, is bigger than OH minus, okay, all this kind of explanation. But again, if you want to memorize, it's up to you. Okay, lattice energy changes more. If the lattice energy changes more, according to this equation, okay, if you know how to apply this equation, it's very good. If you just want to memorize, it's up to you also. Okay, lattice energy changes more. If that happens, okay, if lattice energy changes more, which is going to become less exothermic, your enthalpy of solution will automatically become more negative. Okay, it's explained using this equation. Now, when that happens, okay, it is going to tell you that the solubility will increase. Okay, solubility is increasing. But of course, we are not there to just write down our answers. Okay, we want to learn. Okay, so how if they ask this question related to sulfate? Now, sulfate is going to be, and your sulfate solubility will actually decrease down the group. But it's going to be, every explanation is going to be opposite to what we have explained for hydroxide. Okay, the solubility of sulfates going down the group, okay, will actually decrease. Why? Okay, the lattice and hydration, okay, the enthalpy of hydration, they are going to become less exothermic. That is actually the same for hydroxide and sulfate. But which one changes more? If your hydroxide, the one that changes more is lattice. In this case, the hydration changes more compared to lattice. Why? This is again related to the size. SO4 2 minus is actually bigger compared to M2 plus. Okay, but in this case, the hydration changes more. And what happens when the hydration changes more? Based on the equation that we look over here, what happens? Your enthalpy of solution becomes positive. And when this becomes positive, okay, you can say that this is going to become less soluble. Okay, less soluble. So this is something that you need to remember. So I came out like maybe how to actually remember or something. I was thinking, okay, hydration, if you're talking about hydroxide, then I can actually remember lattice changes more. If you're talking about sulfates, then I know that hydration changes more. Okay, is there a way to make it simpler? Okay, so I came up with this simple SHL. So maybe how to apply this SHL. So basically, if you have sulfate, okay, sulfate, what happens? Sulfate, your hydration, okay, changes more. Okay, if you have sulfate, hydration changes more. If you have hydroxide, okay, if you have hydroxide, then your lattice energy changes more. Okay, you can actually use this method, and I'm going to use this method also to remember. SHL. Okay, this is going to be sulfate. Okay, then hydration. If I'm using for hydroxide, then I'm going to say this is going to be lattice. So this is something that I'm going to use as well. Okay, next, okay, group 2 hydroxides decompose on heating to give you corresponding metal oxide and water vapor. So here they are asking you which one will decompose easily. Okay, with magnesium hydroxide or strontium hydroxide. But again, okay, in your AS, let's actually have a look at AS, your group 2 also. Okay, your related to your thermal stability. Now, here they are asking about hydroxides. Okay, but we have also learned about nitrates and carbonates. The same explanation also. Okay, thermal stability for nitrate, carbonates, and hydroxide going down the group. Okay, thermal stability, okay, it depends on the polarizing power. This is only in your A2. So if you have a better polarizing power, okay, this polarizing power comes from positive ion. Okay, if the positive metal ion, okay, is small and has more charge, it means they have higher charge density. So if they have higher charge density, they are able to attract the electron cloud. So we call it polarizing the anion. Okay, so they will actually polarize the anion. So what happens? This anion, NO3, CO3, or OH, they get polarized. Okay, when they get polarized, the electron cloud become distorted. So when they become distorted, the bonding between nitrogen and oxygen, the bonding between carbon and oxygen, the bonding between oxygen and hydrogen will become weakened. If that become weakened, it's going to be easier to decompose. Okay, you do not need to have a lot of temperature to decompose them. So it means that in order to do that, okay, the metal cation must be small. Okay, so the top one must be is the smallest one. If you look at group 2, if you go up, go down, then the size becomes bigger. So it means that it's easier, okay, to decompose. It means you require less temperature to decompose at the top, and you require more temperature to decompose at the bottom. So it means that, okay, thermal stability going down the group, okay, is going to become more stable. Okay, they are going to become more stable. Thermal stability increases down the group. Let it be nitrate, let it be carbonate, let it be hydroxide. Okay, and why? Okay, now it's actually related to the polarizing power. But have a look at the marks. Only 2 marks are given. So first you need to answer the question. Which one will be easier to decompose? If I look, magnesium is at the top, strontium is at the bottom. So in your periodic table, so magnesium is going to be will have more polarizing power. Okay, then it will be able to polarize OH, and then OH will be broken easily. It will be decomposed at lower temperature. So that is what is playing in my mind. So what do I actually put it over there? So the answer is magnesium hydroxide. Okay, what else you need to put? Very important. When they say explain, you explain in detail. Okay, what happens? Why this one has uh, more, like for example, polarizing power. I cannot simply say they have more polarizing power. You just need to explain. Magnesium 2 plus, okay, is smaller. Okay, magnesium 2 plus is smaller. Okay, of course you don't compare with the charge, because the charge is the same. So you say because of that, okay, your charge density, okay, not the charge but charge density. Your charge density is charge divided by radius, okay, ionic radius. So charge density is going to be be more. Okay, if your charge density is more, okay, so Mg2 plus is able to polarize, okay, hydroxide, okay, and weaken the bond of O and H. Therefore, it's easier or requires less temperature to decompose. Okay, so this is important. Okay, why? Because when you say Mg2 plus here, when you write down, please write down ionic radius. Okay, I don't actually write everything, so I just put ionic radius is going to be smaller. That's going to be the important mark that they mention in your marking key. They want to see the ionic radius and they want to see the charge density. Okay, and then do we need to mention how it will form a bigger or smaller cation? Yes, okay, yes, because it's actually no. When you are talking about why the ionic radius is smaller and so on, no need, Gabriela Nicole. So generally, it is understood. It is at the top. They have Mg2 plus. Okay, they have less number of shells. If you mean that you want to talk about the number of shells, no need, because it's only 2 marks. Okay, because we know for sure 1 mark is given over here. So another one more mark is actually based on your explanation. So I don't think so to explain the ionic radius is going to be important. So, but it's important to say that the ionic radius is smaller, charge density is more, able to polarize and weaken the bond. Even if you look at this, weaken the bond, it's not even in the marking key. Okay, but it is better. Okay, it is better to write it down because these marks can be fluctuated. Okay, if they decide to give you 3 marks, okay, instead of 2 marks, then the weakening the bond will be one of the key points that they will look in awarding you the mark. Okay, so it means polarize and then weaken the bond. So please actually take note as well. Okay, but in this case, no need. Okay, no need, but everything depends on the marks given. Okay, if they give you 4 marks, yes, please explain about the number of shells. But I think in paper 4, they are not going to focus on the number of shells. But in AS, yes, you need to talk about shells. Okay, why the ionic radius is getting smaller and so on. So that is important. Okay, it depends on the level also. Now, if you move further, okay, so the number 3, okay, the overall reaction for photosynthesis is shown. They have given you one half equation over here. So they are asking you to use these equations to deduce the half equation for the reduction of carbon dioxide. So I know that, okay, this is the full equation. Okay, I know this is the full equation. So how did I start? Okay, so I just write down, like, for example, H2O, okay, to give you O2 plus 4H plus 4 electron. Then based on the, okay, just ignore this first, yeah. Based on the question, okay, I know that they want to reduce carbon dioxide. So it means that carbon dioxide must be reduced. Reduce means gain of electron. So it must be gaining the electron. And I know that when I add these two equations, I need to get something like this. So I have carbon dioxide. So I need C6H12O6 because it's not available in my first equation. So I know, okay, maybe it will give you C6H12O6. Okay. So these are the information roughly I have for now. Okay. But what I notice also here, okay, is going to be, I do notice, okay, when I have this oxygen, okay, the oxygen in this case, when they are oxidized, okay, here all the oxygen I think will go here. Okay, so the oxygen is coming out from here, okay, which is going to be the from the water. And I notice from the entire equation there's 6O2. Okay, if I notice that there is going to be 6O2, so what I do is I need to make sure that all of them have 6. So I end up, okay, by multiplying everything by 6. Okay, so I multiply by 6. I multiply by 6. I multiply by 6. Okay, and it is important to eliminate all the electrons. Okay, so 6 times 4 is 24. Okay, so it means I know that this is going to be 24 electrons. I need to get that eliminated. And there is no H plus in the main reaction. I have H plus here. So it means that there is no H over here. There is H here. So it means that this H plus must be eliminated. So 6 times 4 is 24 H plus. So automatically this one will be 24 H plus must be eliminated. So I just put 24 H plus. The rest, I just need to double check everything is balanced or not. Like for example, when I look at carbon dioxide, okay, there's 6. So of course I need 6 carbon dioxide over here, okay, to balance the equation. And then what else I see is going to be, I notice that, okay, water is going to be here. When I times by 6, I'm going to get 12 water, okay, but overall I'm only having 6 water. So it means that you need to actually have formation of water, because if you count, that is going to be to tell us that the water is not going to be enough here. So there's going to be water that is going to be given. Okay, so that water, okay, is going to be, because 24H plus, you only have 12 hydrogen. So here there will be water that is going to be formed. How many? So it means I need to actually form water, so that when I deduct the from 12 H2O, I'm only going to have 6 H2O. So the best way is to put 6 H2O here. So I get something like this. Okay, so this is going to be helpful to tell me that this is going to be my, okay, half equation. So this is how I came about with the formation of half equation. So I need to write down, okay, or every single detail that they have mentioned over here is going to actually help you in coming up with this. If they need you to refer to the data booklet, they would actually tell, okay, refer to the data booklet. So this one, you don't waste time by looking at the data booklet. Okay, it's not there. Okay, now here, but don't expect to actually they tell you every single thing, especially when it comes to measuring standard electrode potential. Okay, sometimes they will tell you refer to the data booklet, but it is understood if they are asking you to calculate, okay, standard electrode potential, you need to refer to the data booklet. So let us see whether they say refer to the data booklet. Yeah, you see, it's good. Okay, it's good that they are asking you to refer to the data booklet, but not all the time. Okay, it is understood. I think certain cases it is understood you need to use data booklet. But in this case, draw a fully labeled diagram to measure the standard electrode potential of O2 in a half equation under standard condition. Include all the necessary chemicals. Okay, so you need to measure standard electrode potential of O2, okay, in half equation 1. So it means you need to write the entire thing. Yeah, so there will be, we are using the hydrogen cell, so it's going to be something like this. So you need to still give the hydrogen. So hydrogen will come in here, and then here will be, please draw nicely. Yeah, so here will be H plus, this is platinum. So this will be H plus 1 mole per dm cube. Then voltmeter to measure. Then again, this is going to be related to half equation 1. So water and oxygen. So you are going to actually relate to oxygen. So again, gas. So you still need another platinum here. So again, H plus 1 mole per dm cube. This one, oxygen. So this is going to actually help us to actually find out what is V. So here from the cell drawn, okay, we know the hydrogen here, hydrogen cell is going to be 0. Everyone should know this, okay. Then you need to actually make sure, okay, do not take the wrong, okay, do not take the wrong equation from the data booklet. Okay, the data booklet, we want the information related to water, H plus and O2. Okay, so you can refer to your data booklet. Okay, that will give you positive 1.23. So I can show you, okay, the data booklet, so that you don't actually make the same mistake, because if you look at the data booklet, there's so many things related to water and O2. Okay, I'll show you. Um, okay, this one, and then there's also this one. Okay, but the one that this one, sorry, this one H2O2. This one, okay, it is important to select which one we want. So we wanted to actually relate it to O2 and H plus. So we want to select the 1.23. So do not accidentally choose something that we don't want. There's so many other things as well. Okay, so you need to refer to what we want. So I want the 1.23. So if I put the 1.23 over there, so this is going to be the E cell. Okay, automatically this is not 0.4. Yeah, so this one will follow this one. Okay, 1.23. And then the identify the positive electrode. This one, please remember, if this one is 0.00 and then 1.23 positive. Okay, so of course this one I told you, the one that is more positive will go to the right. So this one will go to the right. So if you go to the right, okay, the equation that I am actually going to use is this one, O2 plus 4 electron. Now, this is going to be plus electron. If you are gaining electron, is it positive terminal or negative terminal? Charlton?
Negative.
How come? Okay, you study physics also, right? If it is terminal, yeah, okay,
Oh,
terminal, if it is releasing electron, then it's going to be negative terminal. So in this case, this is going to be accepting the electron because you are following this direction. Okay, so if you are using up the electron, this is going to be automatically is going to be a positive electron or positive terminal. So O2 is going to be the one that has the O2 is automatically the positive terminal. Please take note of this. Okay, negative terminal is the where the electron comes out. So the electron will go here. Okay, so this is negative terminal, the hydrogen. So electron will go here and then they will receive the electron over here. So that's going to be positive electron. So please remember that that thing is very important. So now it's already 10. So we only managed to discuss 3 questions. Okay, let me stop.